The last topic that we want to talk about in this section is solving a particular type of logarithmic equation. Now, how do I distinguish later on? I have to use this idea, okay, when everything is mixed up. So when the logarithmic equations can be rewritten as a single logarithm on one side of equal sign and equal to a number on the other side. Then what we're going to use is we're going to use the definitions of a logarithms, okay, to rewrite it into exponential equation and then solve exponential equation. Okay? We're going to use the definitions to rewrite the logarithmic equations into exponential equations to solve. So once again, this can be, this idea, this strategy can be used when a single logarithm on one side and numbers on the other side. That should be that is, okay? So let's take a look at on the first example. Log of base A 121 is equal to 2. So I know that there's a logarithms on one side, a single logarithm on one side, and a number on the other side. So that tells me I can use the definitions. So how do we rewrite this logarithmic equations into exponential equations? But it is equivalent. Base to the second power is equal to the argument, which is 121. So now I rewrote into exponential equations, and I can solve for A easily, which is using the square root property. So when I take the square root on both sides, plus or minus square root, right? Because we are solving quadratic equation now. So A to the second power is equal to 121. So A is equal to plus or minus 11. But you have to be careful with all the restrictions. Since we are solving for the variable A, and then the variable A in the original equation is the base of the logarithm, and we know that the base of the logarithm must be greater than 0, not equal to 1. So my only answer in this case will be 11. That's how I eliminate negative 11 from the solution. Next, example 2. ln of x, that's a logarithm with base e. You have to remember that, okay, that notation, is equal to 7. So I have a single logarithm on one side and a number on the other side. Since ln is log of base e, so recall, right? ln, that is basically talking about log of base e. ln of argument is log of base e argument. So now I can rewrite it as e to the 7th power, that is equal to x. And I don't even need to solve for it. It's already done, right? So you may use calculator to approximate the answer, or this will be the exact value. So my answer will be e to the 7th power. If you use a calculator, then it will be approximately a certain number. Okay. Next. So this time, I don't have a logarithm expressions on one side. So first, what I need to do is subtract 3 to both sides to get my logarithmic term by itself. Right? This is my logarithmic term. So first, I need to subtract 3 to both sides. So log of base 2, 5x minus 1 is equal to 6. I subtract 3 to both sides. Now, this will be exactly look like the definition format. A single logarithm terms on one side, a number on the other side. So I can use the definition to rewrite equivalent exponential form, which is base 2 to the 6th power is equal to the arguments of the logarithm. Now I can solve for x easily. So first, 2 to the 6th power. 2 to the 4th power 2 to the second power, 2 to the second power times 2 to the second power, right? So 4 times 4 times 4. 4 times 4 is 16. 16 times 4 is 64. So 2 to the 6th power is 64, equal to 5x minus 1. Now, solving for x is much easier, which is what? You add 1 to both sides. So that will become 65 is equal to 5x. And finally, divided by x to 5 to both sides, that will become 13. And we need to check, right? According to the previous examples, we know that there is a restrictions in the domain, which is what? The arguments must be greater than 0. So meaning the value of the argument must be positive. So when I plug it in 13, so my argument is 5x minus 1. If I plug it in 13, so 5 times 13 minus 1, that is giving me what? For sure, definitely a positive number. Therefore, now I can conclude that 13 is my final answer. So you need to check. Okay? All you have to do is check the argument is positive or not. That's all. Next question. This one, you want to look at it as a 2 times, let me rewrite it, 2 times log of base 3, 4x plus 3 equal to 6. So I don't have a logarithm by itself. So I need to get rid of this factor 2. So when we get rid of this factor 2, I basically divide by 2 to both sides. So this will become log of base 3, 4x plus 3 is equal to 3. Now we have logarithm terms by itself now. See that before we don't have it, we have this 2 right there. So we need to get rid of it. So that allows me to rewrite equivalent exponential form, which is base 3 to the third power, that is equal to 4x plus 3. 3 to the third power is 27, 4x plus 3. Now I'm solving for x, so subtract 3 on both sides will be 24. And divided by 4 on both sides will become 6. And we need to check. So where are we checking? My argument has to be greater than 0, so plug it into the argument. So 4 times 6 plus 3, that is basically what? 24 plus 3 is 27, is a positive number, so therefore this is a good answer. Last example. ln of e to the third 3x is equal to 6. So in this case, I already get my exponential term by itself on one side already, and a number on the other side. So I can basically use the definitions to continue. Remember from example 2, ln is basically talking about log of base e of the argument. So when I rewrite this into exponential form, e to the 6th power, that is equal to e to the 3x power. Right? Because e to the 3x is my argument in this case. Now, according to the exponential property, if the base are the same and the equation equal to each other, then exponent must be equal to each other. So therefore, I can say that 6 must be equal to 3x. Okay? Because from here to here, we use the property from the previous section, solving the exponential equation. The base are the same. So divided by 3 on both sides, that gives me x is equal to 2. So e to the 6th power is the positive number, so therefore my answer will be 2. And this concludes this sections. And in the next sessions, we're going to talk about, okay, in the future sessions, we're going to talk about multiple logarithm terms on both sides of equation.